So this is the first of 8 videos for reviewing for the final exam for Physics 12. This is the one for our first unit when we were looking at vectors and how we could use them for ramps and for projectiles. And so this works off of the about 30-page handout, and we're starting right here on the first page. We're going to begin by taking a look at free body diagrams, what should go on them and what should stay off of them. So there are two boxes here. They're connected by a rope. It's a bit of a rough floor. It's got a coefficient of friction there. And somebody is pulling up here with this 200 Newton force, but they're pulling at an angle. And the first thing we're going to take a look at is just what does the free body diagram look like for that 12 kilogram box that's over on the right. So hey, it's all about kind of thinking about what's important for the course, not so much important for this one question. Free body diagrams. For those things, we want to put onto them all of the real forces. And I say real because there's one force there that's not real that we really want to keep off of the free body diagram. So you do not want to put on your free body diagram anything that says F net. F net's an idea that we're putting together all the forces in our mind and seeing where that goes with F net equals ma, but it's not real and it should stay off the diagram. Also, don't get lured into putting in velocity. Just because something is moving, don't think that you have to add an arrow in there for that. Moving is not a force. So for this one, this free body diagram, I'm actually going to do it over here on the right. It is 12 kilograms, and in no particular order, here are the forces that are acting on this 12 kilograms. One of them is the force of gravity, so that's going to be going down. We're going to have an mg force there. It's going to be awfully close to 120. In fact, I think when I checked that out, it was 117.6. Now, in grade 11, we would have just said, oh yeah, the normal force, it's going to be 117.6. But no, that's not the case here because of this angled applied force. So there's an FA that's 200 newtons. But that's troublesome because of the way that it's at an angle. So we want to take a moment and rethink that 200 and break it up into some parts. We're going to break it up into a part that goes over, trying to accelerate the boxes sideways, and a part that goes up, which is actually going to be helping to hold this box up so the ground doesn't have to push quite as hard. So for the sideways ones here, it's good to know that there's a 30-degree angle between the 200 and the ground. And now I can just go to my calculator, grab a little help from that, and say, oh, okay, I want that horizontal one, and it's got a 30-degree angle compared to the ground. So 200 times the cosine of 30, and I've got 173.2. That should be plenty of digits. And up and down, 30 degrees is actually a really nice number for doing sine. So 200 times the sine of 30, it's kind of beautiful. Sine of 30 is a half, so I get exactly 100. Now that 100 number is interesting because that 100 is helping to hold the box up. So when I go and think about this normal force now, it doesn't need to be very big at all. I've already got 100 newtons going up. I need to balance out the 117.6 down. This normal force is not 117.6. It's actually only 17.6 newtons. I'm going to have a couple of forces going back. One of them is going to be some friction. I have to think about how much that's going to be. Force of friction, it's just the coefficient of friction multiplied by the squishing force if it's sliding. If it's sliding, then for sure that's how much friction there is. And it's going to be sliding, so I can take that 0.4 and I can multiply it by that 17.6. Not going to be a lot of friction here, just 7.04 newtons of friction. There's another force in there as well on this box. There's also going to be, I'm just going to randomly grab some other color here, there's going to be a interaction force between this 12 kilogram box and the other one. There's going to be a tension in there. And right now I have no idea how big that tension is. For finishing this problem, we're going to have to do a free body diagram of the other box too. I'm actually just going to do that one up here. There's the tension. It is exactly the same size as that tension we've just drawn on the 12. That's just Newton's third law working for you. Has to be an equal and opposite reaction force. There are going to be a couple of up and down forces here. This one, unlike the 12, which has that weird 200 pulling at an angle, this one doesn't have any weird rope pulling at an angle problems. So when we go to find the mg, and we find it's almost 180, right? G is pretty close to 10. Get 176.4 newtons. The normal force here is actually just going to balance that out exactly. So we're going to have 176.4. And this one's going to have some friction. In fact, this friction is going to be pretty substantial because of all of that normal force. So when we check out the friction here on this one, again, just going to be going mu times Fn. If it is sliding, you can definitely use that. And it is. So what do we got here? 117, sorry, I lie. 176.4 times 0.4. That ends up being 70.56 newtons of friction. And that one's now pretty much ready to go. So, free body diagram. You want to draw all the forces that are real. Don't get lured into putting in velocity, and don't put net force on there. Net force is an idea. Now we're heading into question 2, where it says, okay, can you find the acceleration of the system? We're going to do F net equals ma. The really neat thing about F net equals ma, and this is the reason why I've got this question on here, is just how flexible F net equals ma actually is. You can apply F net equals ma to any part of this problem you want, or even the whole thing. I could do just the 18, just the 12, or I could do all of it. I could do all 30 kilograms. Now for this one, we're actually looking for acceleration. I don't know the tension on either of them. They're the same, but I don't know them. I don't want to have two unknowns, tension and acceleration. So this just happens to be one where it actually works really well to take a look at the whole system. We don't always start with the whole system, but I like doing that on this one here because I can avoid the tension. So if I go to do F net equals ma for everything, I like to put F net, all the forces over on the left, and then I can put my masses and accelerations on the right. So for this thing here, as far as left and right forces go, I can see part of the 200. There's this 173.2 that's pulling to the right, and that's it, going to the right. It does win, and it's fighting against the 7.04 of friction, and it's fighting against the 70.56 of friction. There are two tensions in there, but they actually cancel each other out perfectly, so we don't have to worry about them at all. So for my net force, I have 173.2, and it's fighting against 7.04. It's also fighting against 70.56, and that's going to equal, I have to put the whole thing in here. I've got to put all 30 kilograms, right? This is the 12 plus the 18. Got to put that all in there, and then the A. Just, incidentally here, just seeing what the numbers look like when you work from left to right, doing your subtracting, we get 95, or right around 95 newtons of net force. That's going to make that 30 kilograms accelerate. That 95 number, it is nowhere in the picture. It is not a real force. It's just an idea that we use in order to figure out things like acceleration. Okay, so you divide, and we end up with a number, I'm rounding a little bit, but it's right around 3.19. meters per second squared. There's more force to the right than there is to the left, so this thing actually accelerates off to the right. So we can use F net equals ma. Sometimes you do the whole system like we just did here. That lets you avoid tensions. Other times we're going to do just one of them because we want to bring the tension into the story, and that's what's going to happen in question 3. So for question 3, we're going to try to find out how much tension there is in that rope connecting the two blocks. For this one, I'm going to do F net equals ma, but I'm going to pick just one of those boxes. I want to see that tension show up. I don't want to see like the whole plus T minus T thing happen where they go away. You can pick either box. It really does not matter. I'm going to actually go and do F net equals ma on the 12 kilogram box. So it has 173.2 newtons of pull forward, that part of the 200 rope force. There is a friction back, and there's this tension going back. And now I want to bring that in. Okay, so I've got my tension in there, and it's going to make just that 12 accelerate at 3.19. There's now only one thing missing. I know the acceleration already because I've dealt with both boxes to find that 3.19 number, and it's just a case of sloshing the numbers around. Tension's just a force, so when you're done, as always, we're going to go 2 or 3 sig figs, 128, but it is a force, so we're just going to say newtons for our units for that. So F net equals ma. Feel welcome to pick just one object. Feel welcome to grab a couple of the objects or all the objects, depending on how many you see. Mix and match whatever works so that you have just one unknown when you're working with your equation. For our next question here, we're going to be taking a look at a ramp question and seeing how we can actually use vectors and breaking them up for that. A little review of how that deal works. So it's a story about a 2 kilogram brick. It's up at the very top of a roof. It's going to slide along the roof, so it will be moving. It's got an initial velocity of 0.5 meters per second, and it's going to slide all the way down that diagonal length of the roof, that 8 meters, 30-degree angle on the roof. Eventually it's going to go flying into the air, but at least at the beginning for this page here, I'm just going to try to figure out exactly what the final speed will be. I'm going to work on getting the acceleration. So with part 4, let's just take a close look at the brick as it's sliding down the roof. It's kind of just all by itself here, and that's actually really what free body diagrams are all about. But if it helps, maybe just kind of sketch the roof in here just a little bit, just below it. So forces that are acting on this object when it slides down the hill. We've got a couple. We've got mg going straight down, and for this one, since its mass is 2, mg is really close to 20. It's actually 19.6. And there's going to be a normal force coming right out of the ground. It's not quite as big as it comes straight out of that surface. It's not quite as big as that 19.6. We'll get a number on it here in just a second. The reason why it's not quite as big, you have to look at that mg as being resolvable into 2 parts. There's a part of that mg, the phrasing we like to say was it crushes in, C for crush, C for cosine, and there's a part of that mg that slides along the roof, S for slide, S for sine. So we've got 2 components here. There's an mg cos theta, because you get the exact same angle up in that top corner as you do for the angle of the roof, and then sliding along, we've got our mg sine theta. Now for the crushing part, I'm rounding a little bit, but it's right around 16.97 or so. And for the sliding part, it's just kind of a nice little thing with the math here again with that 30-degree angle. Sine of 30 is a half, and half of that 19.6, it just happens to be 9.8 newtons. It's just kind of a fluke that we see the gravity number here show up. Okay, so this normal force that's actually coming straight out of the surface of the roof, it is not equal to mg. When you're on a ramp, that is not going to be the same as the mg value. It's actually mg cos theta. It's equivalent to that crushing force. So it's equivalent to 16.97. Sometimes objects have friction when they slide down ramps, sometimes they don't. This one does. Talks about the roof being a little bit rough. So there's going to be a friction force here. The friction force for this item sliding down, it is sliding, so we can go mu times Fn. Hey, it is a reduced Fn, so this is mu times mg cos theta. And if we take that coefficient of friction, 0.4, multiply it by that compression force, 16.97, this friction ends up being around 6.79, somewhere in there, newtons of friction force. That's it. Just those forces. When I go to find the acceleration of this block, I'm going to kind of sever my emotional attachments to this 19.6. I'm going to work with the 16.97 and the 9.8 numbers instead. And I'm going to do that right here. So F net equals MA. I'm going to tip my head and I'm going to look at it in kind of this direction and see which forces are fighting each other. Looks like we've got a 9.8 sliding force and a 6.79 friction force fighting each other. So I'm just going to put that in for my F net story. 9.8 newtons of sliding mg battling against 6.79. I'm rounding a little bit. It's 2 kilograms. And actually the net force ends up being it's a little bit more than 3. It's about 3.01. And it's going to make that 2 kilograms accelerate. And it ends up being, it's around 1.51 meters per second squared. And it's, down along the roof, right? It's going to pick up speed in that sliding down along the roof direction, like diagonally down. So now we can use that to figure out how fast this brick is going to go when it finally gets to the bottom of the roof. And that's our next question here, question 6. So this actually kind of goes way back to, Physics 11 actually, when we were doing VI, VF, DAT questions. Still a nice part of Physics 12. Don't be shocked to be able to do some nice, easy VI, VF, DAT questions on the test. I am going to call for my question here kind of down along the roof positive because everything's going that way. So my initial velocity, according to the story, was a positive 0.5 meters per second. They'd mentioned that. I'm looking for VF. I'm going to go for a distance of 8. And we've now found the acceleration to be, rounding a bit, but around 1.51 meters per second squared. Kind of trying to avoid time for the moment. Don't have a stopwatch on it. So it looks like we could go with VF squared is equal to VI squared plus 2AD. So it looks like we've got VF squared is equal to 0.5 squared plus a 2, rounding a little on this 1.51 number, and then the 8 meters. And when I tried that out, when I took a square root, rounding a bit, I got 4.93 meters per second. That's how fast that brick is going to be sliding along the surface of the roof when it gets down to the bottom of the roof. And this brick is about to become a projectile, and that's what we're going to take a look at for number 7. So we want to kind of get ready to do our usual projectile table, and like that vertical and horizontal table. So I want to take that 4.93 number and kind of rip it apart into its components, because you see the bottom corner of the roof down in the soffits or whatever they call it, when that brick is about to come flying off. It's coming off like this. I've kind of exaggerated the angle on that roof a little bit. It's a 30-degree angle in there. When that brick comes off the roof, it's going to be going in a direction that actually follows the roof. So this number here is your 4.93. I've rounded a little bit on that number. And we're going to take that and say, okay, that's great, but if we want to do our usual method for projectiles, it works really nice to be thinking about left and right and up and down. Kind of got like a little X shape going on with the angles. I think the math people call that vertically opposite. So that's a 30-degree angle in there. And it looks like we can get at these components pretty nicely here. This one, this Vx, I'm going to call it, that's going to be 4.93. Trying to find the sideways part, so I'm going to go with cosine of 30 degrees. And that ends up being, I think, 4.27 meters per second. And the up and down part, when that brick first leaves the roof, Vy is going to be 4.93 times the sine of 30 degrees. And that's 2.47 meters per second. Kind of heading downwards, right, towards the ground. The 4.27 number, when we do start flying, is actually totally stable, won't change at all. But the 2.47, that one's dynamic. It'll start to grow right under the influence of gravity when we start flying through the air. For question number, well, actually the rest of them almost here, 8, 9, and 10, we're going to be taking a look at how long it takes and how far we're going to go, and we basically really need that table. You can't go wrong with that table that we did in Physics 11, so I'm going to set it up here just so that I'm ready to go for, in fact, all the rest of this 8, 9, and 10 trio of questions. Doesn't matter which column you put where. I'm going to go vertical here, horizontal beside it, and I've got VI, VF, D, A, and T. And when we're flying through the air, I know for sure that the horizontal acceleration is nothing, doesn't accelerate at all. Vertically, it's under the influence of gravity. Now, this question, everything is kind of going down in this question. It begins its trip with a velocity down, it goes down for a displacement, final velocity is down, acceleration is down. I'm actually going to call down positive. I think it will actually work out really well. So vertically, I'm going to say the acceleration is not negative 9.8, but just 9.8. I think that will work well. For flying through the air, when we first start launching, the initial vertical velocity, we're heading down at 2.47, so we're calling that a positive. So 2.47 goes in there, and we're going to be heading sideways at 4.27. Kind of the same number showing up twice there. The displacement for the brick vertically, that's it falling down from the roof down to the ground. And if we look back at the picture, it looks like it's got a wall height there of 4 meters. It is going down, but we're calling down positive, so I'm going to put a 4 in there. And they want us to try to find the time of flight. For the moment, I'm just going to stay away from this vertical VF. Might come back to it in a minute. But for now, I'm going to go for that time of flight. And I think we can get there using d is equal to VIT plus 1/2 AT squared. You should be ready to use quadratic formula on the final exam. It's on the formula sheet if you need it. You're welcome to have it in your programmable calculator if you want. So I'm going to put in my 4 meters. My initial velocity there is going to be the 2.47 t, and then I've got 1/2 9.8 t squared. Got to get everything sloshed over to one side in order to use the quadratic. So I'm going to go 0 is equal to 4.9 t squared plus a 2.47 t minus a 4. It's quadratic. I'm kind of expecting a couple of answers. One will probably be kind of silly when I do it, but we'll see what happens here. So, quadratic program. We're running. Going to go with an A value of 4.9, a B value of 2.47, and a C value of -4 after I moved it over there. I get a couple of numbers. The negative one doesn't make a lot of sense, so I'm going to go with the positive one. This thing is going to fly for 0.686 seconds. And I can now go put that in my table. Hey, another thing I can put in my table is this horizontal final velocity, 4.27. That is never going to change. So that just leaves us with a couple of spots left in the table. Number 9 is how far does it go sideways? The horizontal D right here. So let's do that. That's actually pretty easy to do now. Sideways, it's such a boring story. It's just D is equal to VT. So our sideways range, our D, we've got a sideways speed of 4.27 all day long. We're only going to fly 4.686 seconds, kind of rounding a bit on both of those. And I believe the answer here, if you want to go to about 3 sig figs, is something pretty close to 2.93 meters. You know, if you want to be thorough, we can go back. We could put that in here. Yeah, we've got 2.93 meters. And then we get to question 10. What is the velocity at impact? Be careful with this one. Velocity is a vector, so you have to respect the fact that this is actually asking you all about how does that thing go in and strike the ground at an angle. Like what's its speed on that angle, and what's the actual direction for that impact as it goes. So you're going to find that this brick actually strikes the ground kind of doing something like this. It's got some nice impressive speed at some kind of interesting angle. I don't know the speed right now, and right now I don't know the angle. And the way that I'm going to get there is by relying on components. You say, okay, well, how fast is it going sideways? Which actually I know that number already. And at the moment it's about to hit the ground, how fast is it going up and down? So the Vx, we actually know this one. It has never changed. Once it started flying, it was 4.27. But the Vy, that vertical dropping final speed, I don't actually know that. So I'm going to go and do a horizontal calculation here. I'm going to run with Vf is equal to, sorry, not horizontal, vertical. Vf is equal to Vi plus At. That Vf vertically is going to be my original velocity vertically. I remember I'm calling down positive because everything's going down. So 2.47. And then we're going to accelerate. And we don't have very long to accelerate for, only 0.686 seconds. And when you do that, you find that this object, this brick, is actually descending downward vertically at 9.19 meters per second. I can add that to my picture here. 9.19. You know, if you want to be super thorough, you could go and add that back to my table back up here. 9.19 is going to be our downward speed just before we touch the ground. But that's only the vertical component. And this question said, yeah, but what's just the velocity at impact? So we've got to do a little Pythagoras, got to do a little tangent backwards. Okay, so we're going to rely on both of those ideas, right? The idea of Pythagoras. We're going to use tangent. We're going to take both of those ideas in order to put them together. We've done this a lot. You just can't forget to do it. So that final velocity just before impact, it actually ends up being around 10.1 meters per second. That's how quickly it hits. And there's a direction to it. When you use tangent backwards, you find that it's actually a 65-degree down angle. I wouldn't call it south of east. I would say below the horizon. Be careful with this question. You know, it did ask for velocity, so we had to go with a full deal diagonally. If the question had just asked for what's the magnitude of the velocity, then you would have just said 10.1. You wouldn't want to say 9.19, but you'd say 10.1. So this is the magnitude. And in this particular case, the magnitude of this vector, magnitude of velocity, is just called speed. So be careful. If they had said, what's the speed at impact? You've got to respect the fact that that's a diagonal question and actually give an answer that's 10.1. Okay, final one for this particular day. Here's a kind of a crazy one. It's got a whole bunch of different boxes on the go here. It's going to get really busy, so sharpen your pencils on this one. All the boxes are 8 kilograms, and it does look like there's some friction in there. And the question is, can you find the acceleration for the system once you let it go? And the answer is, sure we can, but it is going to get a little bit messy. The center box isn't too bad. It's going to have an mg going down. The mg on that one, it's really close to 80, because g is really close to 10. It's actually 78.4. And since its ropes are pulling sideways and it's on a flat hill, the Fn for this one is also 78.4. The other ones, they're a little messier. I'm going to do the one on the right first. This one has an mg going down. It's also 78.4. But I'm going to break up that 78.4 into two different vectors. I'm going to have one that crushes in and one that slides along. So C for crush, C for cosine, S for slide, S for sine. And if you use that 35-degree angle, if you use the cosine of it to find the crushing part, the part of that 78.4 that crushes in, it's around 64.2. And the sliding along part, it's right around 45.0, pretty close to there. So for the normal force for this box, it actually ends up being only 64.2. Okay, I've left friction out. I want to kind of see the whole battle first before I get the friction going on in there. The other box, let's take a look here. It's going to have an mg going down. It's also going to be 78.4. And that mg going down can be broken up into two parts. There's a part that crushes in. I'm going to use cosine to find that. And there's a part that slides along. And if I use cosine of 70, I can see that the crushing in component of the 78 is actually 26.8. And the sliding along part of the 78, it's pretty impressive. It's actually 73.7. So the normal force on this box, it has to just battle against that crush. It's going to be 26.8. Not very much. Okay, so there are a few forces I haven't drawn in yet. In fact, there are 3 friction forces and 4 tension forces, quite a few. Let's go with the friction forces first. At this moment, when I stare at this picture, I'm noticing that this 73 is actually more powerful than the 45. They're in a battle. The 73 wins. So actually this way is the winning direction. I'm going to call that way positive. And friction, well, it kind of roots for the underdog. So friction is actually going to be going back on all these boxes. There's going to be a friction here, a friction back on this one, and a friction back on this one. And each time, because it is sliding, I can find that force of friction by going mu times Fn. That'll work great. And I tried that out 3 times, and here's what I found. This box here does not have a lot of crush to it, and the force of friction is around 2.7 newtons. The coefficient is just 0.1, so it's a tenth of the normal force. Force of friction on this one, well, it's around 7.8, right? It's like 7.84, of course, so it's around 7.8. And this last one, the force of friction on this one, it's around 6.4. Now there are some tensions, but you can ignore them, right? There's a tension here and an equal tension there. There is a tension here and an equal tension there. We can ignore them if we do F net equals ma on everything. So for my final calculation on this little bit of review, I'm going to do F net equals ma on the entire deal, which means I'm going to put 24 kilograms in for the m. Now, the F net. Whew, it's crazy. The 73 is battling the 45, and then friction is coming to the aid of the 45. It looks like we're going to have 73.7 in the winning direction, and then everything else is against it. There is a 45 that's against it. And there are 3 frictions that are against it at 2.7, a 7.8, and also a 6.4. That is trying to make all of this mass accelerate, all 24 kilograms. And so when you're done, I think the net force is somewhere around 11.8 newtons. And that's trying to get all 24 kilograms accelerating. Okay, so we divide, and I think it's around 0.49, somewhere in there, meters per second squared. A bit crazy, but it worked out. You're allowed to do F net equals ma on a little bit of it or on all of it. I chose to do all of it. Always thinking about C for cosine, C for crush for that mg part that goes into the hill, and the Fn's the same as that. And then S for sine, S for slide for the slippery part of gravity trying to get it along the hill. And this is the end of the first chapter review.